Good morning, everyone, and a warm welcome on behalf of the Wilhelm Heraeus Foundation to this Breakthrough Symposium this morning. It's a pleasure to be here and say a few words about the foundation. For those of you who joined us for dinner yesterday, they already learned quite a bit about the foundation, but I hope that I'm able to add some further information. So first of all, who were Wilhelm and Else Heraeus? Wilhelm Heinrich Heraeus was born 1900. He studied physics, mathematics in Bonn, Göttingen, and Munich, and then he moved to the University of Frankfurt, where he completed his PhD in physics in 1923. So at the age of 23, which was not uncommon at that time. In his CV, he writes that his advisors were Herr Geheimrat Wachsmuth and Herr Professor Gerlach. So this is, of course, Walter Gerlach, who today is best known for the famous Stern-Gerlach experiment, the first experimental demonstration of quantization of angular momentum. So these were the exciting years where quantum mechanics was developed. And you know, we are this year in the International Year of Quantum Physics. But Wilhelm Heinrich decided to leave academia, and he entered the company his grandfather has founded in 1851 in Hanau, a small town some 30 kilometers east of Frankfurt. And he spent his whole professional career as entrepreneur and manager in this company. As he and his wife Else had no kids, and they decided in the 1960s to found this foundation. After they passed away in the 1980s, all their company shares were transferred into the property of the foundation. And today it's the dividend of these shares which constitutes our regular income. So if the company makes money, they pay us a dividend. It's good for us and it's good for you because we can support and fund activities like this symposium and many others. So as the money comes from the company, let me just say a few words about it. It's a globally active company. One of the top 10 family-owned companies in Germany, which includes business in different sectors. And just to give you two examples which are very strongly related to physics. Heraeus delivered several tons of ultra-pure niobium for the superconducting accelerating cavities, both of the Large Hadron Collider at CERN and the European X-ray free electron laser in Hamburg. And another example, the right picture shows two of the mirrors of gravitational wave detector LIGO, and the blanks of these mirrors were also manufactured by Heraeus. So now coming to our activities, we do support research and education in science with an emphasis on physics by, for example, funding school activities like school labs. We fund teacher training courses. We support early career researchers with a whole bunch of different activities. We organize and fund scientific events. We cooperate very strongly with the German Physical Society, DVG, and there are many other activities I'm not going to mention in detail. Just to give you a glimpse about some activities related to education, so we do fund school labs. For example, there's a picture here showing a school lab dedicated to environmental physics and spectroscopy. Many activities are also related to astronomy. We do fund different prizes and competitions like Jugend forscht in Germany, and we fund and support teacher training courses in order to bring more modern physics to schools. Then another big group of activities is related to scientific events like the Heraeus seminars, which are often compared to Gordon conferences. So there are 60 to 80 people, workshops with seniors and early career researchers on all topics of physics and interdisciplinary areas. And more recent activity are the binational seminars. Here the idea is to initiate new or foster existing collaborations between working groups in Germany and the partner country. We started this activity with European partner countries, but meanwhile extended it to other countries, especially from the Global South. We had several seminars meanwhile with Brazil, on Argentina. We'll have one with South Africa and others. Many of these activities take place at the Physikzentrum in Bad Honnef. It's a wonderful conference center, and I'm sure many of you have been there before. But we also support many activities at other European conference centers like the École de Physique in Les Houches, or the Ettore Majorana Foundation in Erici, and recently we also started a cooperation with the International Center for Theoretical Physics, the ICTP in Trieste. Finally, I just want to mention a few activities related to early career researchers. Almost 10 years ago, we started activity called Leading for Tomorrow. So it's a leadership program for early career researchers. This is run by the German Physical Society, financed by us. And next year, there will be the 10th year of this activity. And I know that several alumni of this program are here as well today. Welcome. We also started 2 years ago a program, an internship program, where PhD physicists with PhD can spend 3 months in the German Parliament. It's also a very interesting program, and I know that there are also some of these here, so welcome again. And finally, 2 days ago, we had our annual meeting, the so-called Heraeus Forum, and for the first time, we awarded 5 young researchers with the Heraeus Research Fellowships. The idea is something similar to the Alfred P. Sloan Research Fellowships in the US, and here we want to support young researchers who are not yet tenured, but already have a very promising career, and this is one of our latest activities. So my time is almost over. I hope you enjoy as much as possible this symposium here, and before I end, I want to say thank you on behalf of the foundation to you both here, Thomas Elsässer and Jükdem Esivir, for organizing and chairing this session this morning. Thank you very much.
Okay. Good morning, everybody. So I welcome you to the symposium on this early morning on Saturday. I'm Jükdem Esivir. I'm a particle physicist, experimentalist. I'm working at the Atlas with the Atlas experiment at the Large Hadron Collider since many years. And I'm with the Humboldt University of Berlin and DAISY, which is a Helmholtz Institute just right outside Berlin. So that's me as a person. I'm looking forward to this symposium very much. Thank you.
Okay, so also warm welcome from my side. I'm Thomas Elsässer. I'm with the Max Born Institute here in Berlin. My field is ultrafast optics, spectroscopy, and also structure research. And it's my pleasure to chair this symposium now, I think, for the 4th time. And the format is kind of established, but I will just explain to you what we are planning for this morning. So the program has essentially 4 parts. We start with a session of longer talks, longer means 8 minutes, by the finalists of the physics competition. And then after the coffee break, we have next generation researchers with even shorter talks. And this is followed by a short panel discussion about astrophysical perspectives. And then after that, you are encouraged to approach our speakers. And to do this, we'll organize 3 speakers' corners, topical corners. You are free to choose the topic you want to have. And this is your opportunity to get in close touch with our speakers to discuss trends in the fields, in the respective field, to discuss challenges, and in particular also to discuss how younger scientists can be part of activities in this field and how they can integrate their research in the bigger framework. This is roughly what we plan for today. Okay, so let's get started with the finalized pitches, and our first speaker will be Henry Chapman from DAISY. His title is Observing Molecules in Action. Henry, please.
Okay, life, it turns out, is pretty complicated. Oops, this is working, it's not running. So most processes in life are driven by macromolecular machines, such as this one you see here. This is DNA polymerase, which is replicating DNA. And today, using AI programs such as AlphaFold, you can actually predict molecular structures, protein structures, from their genetic sequence. But these are static structures obtained essentially through measurements of crystals at cold temperatures. So to make movies like this, it's a lot of imagination, but also sort of seeing how these objects fit together. And what we'd really like to do is to really watch proteins and other macromolecules catalyze reactions and interact with the environment, and learn how to really design functional proteins. So to do that, we need good tools. Even the best optical microscope you can get can't see molecular detail because the wavelength is too long. So we need to lower that down to the size of the distances between atoms, and that's X-rays, also electrons. But the trouble with this is that this radiation is very energetic, it's ionizing, and breaks bonds, and essentially destroys the very sort of protein or structure that you're trying to see. So it's a little bit like being in a very dark room, kind of like this one, and having kind of a secret message on light-sensitive paper. So to read the message, we have to turn on the lights, but in doing so, it burns up the paper, so it's very light sensitive. So we can't read the message. So there are, of course, ways around this, and one way is to have a very nice high-end electron microscope, and then put your protein in vitreous ice, so it's cooled down to cryogenic temperatures. And then you get these sort of ghostly images, limited by that radiation damage, essentially. But you can find the images that are of similar orientation and average those together and build up the structure. And this works really nice, and it's great. But again, it is cryogenic, so you can't watch dynamics, and even the act of cooling it down to these temperatures can change the structure. So X-rays are much more penetrating, and one thing you can do that, and has been done successfully, is that you can create large crystals, many billions of molecules, all arrayed in a periodic lattice. And when you shine X-rays on it, that they can interact with all those molecules, and the very weak scattering from each one of them can add up constructively in particular directions. And from these diffraction patterns, you can decode the structure. But now, again, you've got billions and billions of molecules, and it's hard to have them all acting in unison if you want to see dynamics. I mean, we can trigger with optical pulses, but even then, we can't get the optical pulse even through these very large proteins, crystals that are needed to sort of spread out that damage. So we've been looking at a third way to overcome the radiation damage problem, which is to use a fast flash, do flash photography. That way we can read our message, we can take a picture of the message before it burns up, and then sort of look at it as we like. So how fast a flash do we need? Essentially femtoseconds, because that's the time scale for atoms to move. And that's about 1 billion times faster than this picture taken here of a microsecond flash that's stopped this speeding bullet. So our big flash bulb is the European XFEL that was just mentioned. So this is a long accelerator. We need to create extremely energetic pulses that are compressed down to femtosecond duration. So it starts at Daisy and goes all the way into the next state of Schleswig-Holstein. So it's a big machine, big facility, and with that we can record diffraction from small objects that we're just streaming across the beam, constantly refreshing and collecting that data. We started out with sort of tiny nanocrystals of proteins, and we call this method serial crystallography. And with this, we can also trigger reactions with an optical pulse moments before the X-ray pulse comes along. And with that, we were able to watch a particular protein repairing UV damaged DNA. So you see here on the left there, it's DNA, a short strand of double-stranded DNA, which has been UV damaged. So two of the bases have sort of fused together. This protein photolyase recognizes that and repairs it. And what's interesting is it itself is light driven. So light activates the chromophore, this FAD, and which donates an electron. And we can, by doing this serial crystallography, we see that within 3 picoseconds after the flash, there's this conformational change that stabilizes the excited state, so that the electron has time to go and break these two bonds sequentially that are fusing the two nuclear bases. Then the electron is returned, triggering conformational changes that essentially eject those two nuclear bases, so that they can go and bind across as they should to their pairs. And that shows just how effectively and so how quickly this DNA repair mechanism actually works, and explains how that happens. But again, we're having to trigger all these molecules together in synchrony. Even in a small crystal, it's not clear if they all follow the same reaction pathway. So we want to do this really molecule by molecule. Look at single molecules. And with the X-ray free electron laser, when we focus the beam down to extremely small dimensions, we get very strong, intense beams and we can actually measure diffraction from single molecules, as shown on the left there. And again, using these averaging schemes from cryo-electron microscopy, we can build up class averages of diffraction patterns, and then build up a three-dimensional sort of representation in Fourier space of the molecule, and then reconstruct the structure that you see there on the right compared to the known crystal structure. It's still pretty low resolution today. This is fairly new data. But so we're kind of like where electron microscopy was maybe 30 or 40 years ago. But we're very excited about this, and it's very encouraging because now we'll be able to sort of piece together the reaction. We can sort of really take one molecule at a time, figure out how it relates to others in the sequence of, and really see how molecules are functioning and how they function, and learn how to design new functioning proteins. So thanks.
Thank you, Henry, for this nice overview. Are there questions? Here.
Thank you very much. Really nice talk. I would have a question on the right image shown here on this donut-like structure. The DNA strands are visible on the surface of this donut-like structure. Is it also possible to visualize the internal structure as well?
Yeah, certainly. So we get a full volumetric image. So it's so we've captured the molecule in all orientations, so we can piece that together. I didn't mention that this is a heme complex from worms. It's quite a large thing, but we can cut it through, and we do see some variations in there. And the idea is that this heme complex has some dynamics that happen in the way the components are arranged, and we hope to be able to sort of capture that.
Okay, we have time for one more question. Maybe I can ask a quick one. Can you integrate water molecules in the crystals? Because the native environment of the DNA is, of course, aqueous.
Right, that's right. So currently we're sort of aerosolizing these molecules, as shown here. And what we'd really like to do is keep them in an aqueous environment. So people are developing these very ultra-thin liquid sheets, jets, that are only 10 centimeters. There's actually a lot of work being going on at SLAC on that. So if we can keep them in that environment, the water will add some sort of background, and so we've got to deal with that. But I think that's the way to go.
Okay, thank you.
Thanks.
Also, thanks again. Our next speaker is Claudio Emma from SLAC, And the title of his talk is Intense Particle Beams. Claudio, please.
Okay, so good morning, everyone. It's really an honor for me to be here among so many illustrious colleagues to present the work that we did this year on making the world's most intense ever electron beam. So I just wanted to start by giving kind of a quick overview of the context for those of you who are not particle beam physicists by trade. So particle beams are really unique tools for discovery and fundamentally very powerful probes of the natural world. So if you look historically over time at the amount of discoveries that have been enabled by particle beams, they are really now becoming ubiquitous technology we use everywhere in our daily lives. So starting from the 1890s, the discovery of the X-ray, going with more intense beams to the discovery of the nucleus, and then on, marching through the decades, all the way towards completing the standard model of particle physics with the discovery of the Higgs boson at CERN. So what you can see is that there's one through line here. The beams get more and more intense. The more intense they get, the more we can see deeply into fundamental processes in nature. And of course, particle beams started as tools for fundamental physics discovery, but nowadays, if you look at applications, they're everywhere from hospitals to, for example, imaging, as we just heard in this talk. Everybody sees the COVID virus here imaged at synchrotron facilities. And then even looking at things like historical artifacts, so you can use particle beams to look at scrolls by scattering, for example, light off of different kinds of inks and read where you could not. So they're really fantastic tools for discovery, but what is exactly special about intense particle beams, and who are the users that want more intensity today? So obviously don't have time to go into detail with all these applications, but I wanted to give you a flavor of the breadth. So there are many communities right now that are looking at the particle sources out there and saying, well, we want more intensity. And what does more intensity mean? It just means more particles packed into a smaller volume and compressed to shorter time duration. So just to give some highlights, there are new collider concepts out there that want to look at boiling the quantum vacuum. They want to look at quantum electrodynamics in this non-perturbative limit. So we have theories for what goes on there, but we really don't have any experimental way to access this regime right now. Having more intense particle beams would enable that. There are concepts for attosecond light sources to go even shorter than the pulses we can make today, to tens of attoseconds. This would allow us to basically have the world's fastest camera and resolve the motion of electrons in atoms on their natural timescale. Incredibly powerful. The list goes on: laboratory astrophysics, strong field QED. I just want to mention one that's near and dear to my heart. So intense particle beams can be used as drivers for advanced particle accelerators. So you can imagine taking a beam, colliding it with a plasma source, and exciting a large amplitude plasma wave. In this large amplitude plasma wave, the fields are just enormous. And you can use these fields to accelerate a second particle beam in just a fraction of the distance of what you can do with conventional technology. So this could really revolutionize both high-energy colliders in the future, but also just democratize access to particle beams, making a lot more university-sized accelerators feasible in the future. So then comes the challenges. So I guess, why don't we have these beams today in the lab? Is it just that we're bad at our jobs and we can't make them intense enough? Well, the answer is not really. It's really difficult to compress particle beams. And I tried to summarize that in the cartoon on the top of the slide. So the conventional paradigm for compressing particle beams involves using this sort of trick that I'm illustrating here in the top cartoon. So you start with a bunch, say it's many, many electrons, and you accelerate this bunch, but don't give all the electrons the same energy. So you give it this time-energy correlation. So the electrons at the back have slightly higher energy than the ones at the front. Now you send this beam through an array of magnets, and because the Lorentz force bends the particles differently, the high-energy electrons get bent less than the low-energy ones, and so the high-energy ones catch up. And in the end, you end up with a compressed bunch. So this paradigm works great, and it's used at many facilities, XFELs all around the world. But as you start to increase the number of particles in this bunch, the particles will radiate as they bend through the magnets. And this radiation will actually act back on the electron beam, spoiling the beam quality, diffusing it. So you end up with this kind of beam that looks like a snot ball, which is illustrated on the right. And you can't use this for applications. So that's the first challenge you have to overcome. The second challenge is that suppose you can make these very intense beams. Now, how do you measure them? Well, typically, we take beams, and to measure where they are, how big they are, we collide them with solid or gas targets. But But usually when you collide beams with targets, they don't do this stuff at the bottom. They don't turn it into Swiss cheese or drill holes in it. When the beams become intense enough, this happens. So you have to fix this problem. So we had these two challenges that we wanted to overcome, and we did an experiment at SLAC where we tried to make the world's most intense beams by doing things slightly differently. So the first thing we did is we, instead of using the radio frequency cavities to modulate the chirp on the entire bunch, we use a laser to impart a very, very localized modulated energy inside the beam. So the reason that lasers are good is that they enable you to control the chirp. You can get a very large amplitude chirp. You can also only put it over a small subsection of the beam, so you can really shape the longitudinal phase space. This means you get more compression with less bending. And that, in turn, makes it so that you can turn this energy modulation into a very large density modulation, in this case, for those of you in the field, with about 100 kiloamps of peak current and 10 GeV. So that's a petawatt of peak power. Now, of course, that maybe sounds impressive to some people, but then you have to measure it. And in order to measure it, as I said, we couldn't directly use conventional diagnostics, so we used non-destructive methods. In this case, we looked at the radiation of the beam after it had been fully compressed right before it entered our beam dump. We were able to use spectroscopy to back calculate using the radiated spectrum what the bunch length needed to be. So this was great. We were very excited about this result, but most exciting of all is that we've already started delivering these beams to users. So as soon as the users at our facility got wind that we were making 100 kiloamp bunches, they said, okay, we have some ideas. And most of all, we've been doing plasma Wakefield experiments, looking at different regimes of plasma acceleration with these beams. So, okay, I think at this point, you know, we're at the stage where, in the talk, where we're patting ourselves on the back maybe, and we're saying, okay, we have very intense beams. That's great, but what's really next? So if you look at the roadmap for accelerator and beam physics and the applications that I was discussing earlier, they demand ever more increasing intensity, some of them more demanding than others. For example, for the collider, 100 kiloamps is not enough. You want maybe 1 megaamp. So we need another factor of 10. And this, of course, has been recognized by the accelerator community, so much so that, at least in the US, a roadmap was published a few years ago, which in its decadal vision listed this as one of the 4 grand challenges for accelerator and beam physics. So we wanted to get to 100 kiloamps in the first 5 years. We can check that off. And now we want to go to a megaamp in the next 5. The good news is that we have some ideas for how to do that. It's going to require completely reshaping the technology once again. So not using lasers to compress the beam, but actually using plasmas. But of course, I don't have time in this talk to go over this, and we don't have any results, but maybe at the next Falling Walls conference, we can talk about megaamp beams. So with that, I just want to close. I have 4 seconds, so I can at least thank my collaborators, especially these 3 of my colleagues who were really instrumental in the experiment, and also thank our funding agency, the DOE, for supporting this research, and thank you for your attention.
Thanks, Claudio. Are there questions, comments? It's hard to see. Yes, please.
Thank you for the great talk. In the beginning, you mentioned the application for quantum materials. Can you maybe comment what the motivation there is?
Yeah, so essentially, with very intense beams, you have a sort of relativistic hammer. And now when you make the bunches short enough, you can basically excite quantum processes in materials. You can look at damage on extremely fast timescales. Now, the really exciting thing is if you sort of pair it with what was discussed in the previous talk. So now you have the beam, which can be the pump, and then you can use that same beam to generate photons to probe. And now you have a system which is kind of jitter-free because you generate the photons and the pumping with the same beam. So this is the kind of experiment we want to do. So going forward, yeah.
Okay. Yeah, I don't see any other questions. Thanks again, Claudio. And our next speaker will be Martin Harmer from Lehigh University, and he will speak about 100 years of superalloys. Martin, please.
Thank you very much. There are thousands of alloys, metal alloys, but very few that can survive extreme conditions of very high temperatures and very high stresses, like, for example, the hot turbine blades in your aircraft engine, like the one shown here. And we give those that can survive the name of superalloys. They're like the superheroes of all the metals out there. The most successful example of a superalloy is based on nickel. Nickel superalloys are the sort of gold standard of superalloys. So let me tell you a little bit about nickel superalloys and then the alloys that we've made to talk about today. So nickel superalloys have evolved over many, many years from being polycrystalline, multigrain, which you see on the left in the figure, to single crystals on the right. Single crystals have much better creep resistance. Creep is the deformation of a material at high temperature. With time under load, it's like the ability to maintain its shape. And so we sacrifice some strength, which you get higher strengths with polycrystal materials, to get better creep resistance. That's a very major property of these materials. The main source of strength in a superalloy, a nickel superalloy, is this. In metallurgy, it's a very famous phase. It's called gamma prime. It's an ordered intermetallic alloy of nickel-3 aluminum. And the picture on the left shows this blocky structure it has. It strengthens the material, and the key to the strengthening mechanism is that it aligns itself coherently, so the atoms align from the matrix. You can see in the picture on the right, they align with that ordered intermetallic gamma prime phase. So it's a very important phase in the development of superalloys in these applications. So now, in terms of what we've done, we've taken the opposite approach to single crystals. So if you can imagine now taking the opposite approach and asking, what can we do if we make the crystalline size of a polycrystal as small as we possibly can, and we build the structure atom by atom in such a way that we can get both high creep resistance and very high strength. And this is just the kind of essence of the things that Richard Feynman talked about in his very famous lecture in 1959, which you probably have all read. There's plenty of room at the bottom. So we've sort of taken some of that advice from predictions, from prophecies from his work. And I would mention too, he did emphasize in his lecture the potential importance of layers and layer structures and building atom structures from layers. So here's what we've done in this work. Although let me first just point out that it was 40 years after Feynman's lecture that electron microscopes became good enough to actually see the atoms to be able to do the things that he talked about. The discoveries that we've made in looking at the individual atoms, shown in this figure here, have shown us that the spaces between the grains in polycrystal materials form very unique, distinct layer-like structures. We actually call those, the term that we use for that is complexions. And these form different layer structures, and depending on the nature of the layer and the bonding in the layer and the number of layers, it can completely determine the properties of the material. So that the difference between one layer and two can be the difference between a brittle material and a ductile material. It can mean the difference between a material that doesn't creep and a material that falls to pieces. It can make a massive difference. So complexion engineering is something that we have now become very aware of in the field of material science and engineering. So in the materials that we've developed, we've collaborated with Chris Darling's group at the Army Research Lab to make a superalloy from nanocrystalline copper. Copper is probably the last material you'd pick to think of making a super alloy out of. It's soft even at room temperature, and the nanocrystalline grains in pure copper are very unstable. They'll grow at room temperature. So we've done this in a very special way, a processing way to make this material. We've alloyed it with tantalum, and made it, tantalum is insoluble in copper, and we've milled it at very high energy at cryogenic temperatures to dissolve mechanically the tantalum into the copper, then annealed it, heat treated it, and it precipitates out a nanocrystalline structure and these really tiny precipitates and nanoclusters, only a few nanometers of tantalum. And it does a pretty good job at pinning the structure, stabilizing it, and giving you reasonable properties. It's a very good start in the alloy development. But there is some oxidation of the tantalum, and there's some growth of the particles, so it's not ideal. So we further modified this composition to add lithium, particularly as well because it prevents the oxidation. Lithium is a very strong reducing agent. And it produced an incredible transformation in the microstructure of the material. So we see an atomic resolution image now of what happens when you further add the lithium. So in the image in the middle of that particle, that precipitate phase there, you can see it's bluish regions. It is reacting with the copper to form Cu3Li, which is gamma prime, which is why I mentioned it earlier. So gamma prime forms as the phase, and the energy between the gamma prime phase and the copper matrix is high, and to lower that energy, it forms a complexion at the interface, which is a bilayer of the tantalum. So it's like it's enclosed, safe almost, as it were, where it's encapsulating that phase of Cu3Li. The properties of this material are quite amazing. So this material can be, first of all, its creep resistance is very comparable to nickel superalloys. Very comparable. It's about 6 orders of magnitude or more higher than the creep resistance of copper without the tantalum lithium. Its strength is about 1,000 megapascals, which is the order of the strength of many steels. And the real benefit of this material is the stability of it. The Achilles heel of nanostructured materials is that they're not stable. This material we heated for 10,000 hours, which is over a year, at 800 C, which is close to the melting point, and the strength dropped by just 4%, still at 1,000 megapascals, and the grains grew only 1 atom spacing every 100 hours. So it's incredibly stabilized. So we're very happy with the results of that superalloy. So we feel that in the future this is paving the way to make perhaps other superalloys of what we'd call unobtainable materials now. And the key to this work was the complexion that formed, the bilayer complexion. So we think complexion engineering can pave the way to make other new materials that have unique combinations of properties. And I would like to end with the acknowledgement of the team effort that put this together. We worked with the Army Research Lab. We worked with Louisiana State University group and Arizona State and various people at Lehigh. Thank you for your attention.
Thank you, Martin. Are there questions?
Sorry, I may have missed it, but how complicated and how expensive is it actually to manufacture this material?
Well, that's a great question, because I think that also is the future. It requires a different kind of manufacturing than is traditionally used, because it's powder consolidation at low temperatures, and the material requires, at the moment, techniques like high pressure torsion or high pressure extrusion processes to make the material. So it will need some modification and adaptation. But you saw from the part in the hands of the metallurgist Chris Darling's group, it was pretty big. So that the ARL have demonstrated you can make much larger, large bulk components out of this material. But it will need some, I think the manufacturing science will be an area of much need. But there's every reason to think that it will be feasible to make large components.
Okay, there was another question over here.
Yeah, thanks. I'm curious to know the modifications that you make to the copper change its mechanical properties. Does it also affect the electrical conductivity?
Absolutely. Actually, I forgot to mention that was a major point. The major point is that the reason we picked copper was because of its higher, actually, thermal conductivity, because thermal management is the key most of the developments in the field of superalloys, especially for aircraft engine, have come through advanced cooling methods. I mean, I don't know if you know it, but the temperature in the combustion chamber is higher than the melting point of the alloy. So if you didn't have that, you'll never fly again if you hear all this. But if you didn't have that, literally it would melt. So it's 4 times higher, the thermal conductivity. So one of the advantages might be things like high temperature heat exchangers. Any situation where you've got thermal management, the copper brings some enormous advantages. So thank you for asking that question.
Okay, I think we have to move on. Thanks again. And our next speaker is Tanja Mehlstäubler from the Physikalisch-Technische Bundesanstalt in Braunschweig, and she will talk about time and frequency standards and probably atomic clocks.
Yes, thank you very much. Indeed. Yes, and I would like to bring you back to the time of 1967. That was a new definition of the second was established then. And it was actually the first time in thousands of years that we went away from an astronomical timescale to a quantum timescale. So we use now for the very first time a quantum system as a natural pendulum, and that is the resonance frequency between 2 quantum states, to define a time scale and to define a second. So the cesium atom was chosen back then, cesium-133, and that is the resonance frequency of the hyperfine states in the ground state. So this is what we take as a current definition of the second. And this cesium clocks has improved by orders of magnitudes back then, and they're omnipresent in our daily life. You can't imagine how everywhere there are basically clocks making your everyday's life, in telecommunication, in financial transactions at the stock market, in the navigation system, on mobile phones. Even in the future, quantum communication will highly profit from clocks because you need also good time tagging to correlate the entangled photons. Now in the 1990s, a new type of clock showed up. We call them optical clocks. So they follow the same concept, but you go a level of energy higher. So that means the resonance frequency we're interrogating is much faster. It's actually 10 to the 5 times faster than the microwave, the cesium clocks. And you can imagine it makes just a much finer scale to measure time. And that's why we can measure them more precise and faster. And so it's not surprising, as you see here, these optical clocks, meanwhile, have overtaken the cesium clocks by almost a factor 100 in the laboratory. So the BIPM established a roadmap how we can potentially now redefine the second based on these optical clocks in the future. However, there's a caveat. There's a lot of criteria still missing to reach this fulfillment and to establish a new second. And I will come back to that in a minute. So, but first I would like to show you some modern applications of this high level of atomic clocks. There are plenty of them again, and for sure we will see them in communication, telecommunication, even 6G and beyond will require definitely in high bandwidth optical frequency standards. But I would like to actually go in here now in 2 types of applications that are a little bit less known maybe. So we're having our quantum system to measure time. And if I measure time, I enter the realm of general relativity, of Einstein's domain. And I think that's highly interesting because I think there will be a lot to be discovered in the future when we measure quantum time, or tests of general relativity, because these 2 theories don't really match well. They don't fit quantum mechanics and relativity. So what we have done in our lab, we've basically established a new type of Michelson-Morley experiment, measuring the isotropy of space. And at the moment, we hold a record of 10 to the minus 21 that Einstein is indeed right. So local Lorentz invariance still holds. And what we replace, basically the old laser interferometer with the modern atomic matter wave interferometer and using the electronic quantum states to measure the isotropy of space at this incredible level. We also used a high-precision spectroscopy in our atoms to do nuclear physics. We can use the electron as a sensor of the nucleus and see how the nuclear shape is changing. When just another neutron arrives from isotope to isotope, we can see in our measurements that the nucleus is deforming and changing by a few femtometers. And then in collaboration with high-energy physics, nuclear physics, astrophysics, we can set new bounds for possible new particles, fifth forces, looking for dark matter. So that was also a recent outcome of this here. Then back to the ground, we're engaging ourselves now in geodesy. You see the geoid, this knödel in the background. So again, we're using general relativity, so gravitational time dilation. There's a nice Bloomberg video if you're interested in that. Time dilation tells you that time is ticking slower at your toes than it's ticking around your nose level if you're standing. And this I can resolve with 1 centimeter precision. My clock with 10 to minus 18 can resolve time differences of just 1 centimeter height level. So we teamed up with geodesists to monitor the world. Yeah, we know climate change is not only melting the glaciers, it's also subsidizing the mountains. The permafrost is diminishing. The Zugspitze is probably shrinking by 1 or 2 centimeters per year, but that was not detectable with classical sensors so far. Now, how do we reach this incredible level? We're using a quantum system that is the most precise quantum system we can have nowadays, only limited by Heisenberg's uncertainty principle, a trapped ion. These are very good clocks, but there's a fundamental problem that they're limited by quantum noise. So if I want to resolve the 10 to minus 18 or even 19, it takes 100 days to reach this. So the projected accuracy is limited by the feasibility to measure it, to resolve it, so noise. And how can we push that? And that's where our proposal came in more than 10 years ago, to scale up quantum systems for time and frequency measurement, for metrology. Not for quantum computation, but to use them for accurate time and frequency measurements. And it was incredibly hard to convince people that this could work. I was very surprised, so I started with a junior research group back then. And there were many worries on one side, but we found solutions on the other side. In particular, we demonstrated that a self-organized crystal and system always organizes itself that the electric field must be zero, because it's stationary, it's not moving. So we don't have first-order time shifts. We built our own ion traps. We studied the complex system of many particle dynamics, heat transport, and how we can cool that. So many things. In particular, I would like to show you here the ion traps that we developed ourselves at PTB. Now we teamed also up with Infineon to bring them on an industry level. These are the beautiful Coulomb crystals that we have. These are ytterbium ions, where you see fluorescing in the light of the laser. And we measure time gradients. We can resolve time gradients and verify that time gradients in our crystals are below 10 to minus 19. So we can make a complex Coulomb system very homogeneous for time measurement. And then after 3 years of evaluating the clock, because if I tell you this is 10 to minus 18, you probably will not believe, so I have to compare clocks. We did this for over 3 years, and actually it was surprising, it was a world record at first shot. So for the first time, our clock fulfilled this mandatory criterion for the redefinition of the second, that we measured time and frequency at the level of 4 times 10 to minus 18 in direct clock comparisons. So that not only made it to the cover of PRL, but had a big impact in the press and so, because it was so important for the potential new definition for the second. So, and for us, of course, it's very important because it was the benchmark. This new concept of a multi-ion clock, of a crystal clock, really works, and we are more than competitive with standard optical clocks. So this is then the future view. What we will do with this new type of multi-ion clocks, we'll go on scale with integrated photonics to bring them up on the mountain for geodesy and many other applications. But this is the very future vision with integrated ion traps, where we work now a lot with industry partners. And yeah, with this, I'm actually a little bit faster than I thought. I'm very happy and looking forward for your questions. Thank you.
Thank you, Tanya, for this fascinating talk. Are there questions?
You've shown this exponential plot of accuracy over the years. How long is that going to continue into the future?
That's an interesting question. Actually, maybe it depends on the interpretation of the viewer, but you might see a leveling off when you look at the zoom up here. So you see the cesium clocks are already leveling out, the 10 to minus 16. This is fundamental. This is collisional shifts. Yeah, it depends now on the interpretation if you see the same effect happening here at the optical clocks around 10 to minus 18. I'm pretty sure we will make it down to 10 to minus 19. There's already like a clear path. We already published a paper in 2019 how we can reach the 10 to minus 19. You always can estimate the error budget and say, I have to do this. I have to cool further from millikelvin to microkelvin. We know how to do it. So I think 10 to minus 19 is reachable. Then we don't know. Then this is like looking in the glass bowl. What other new effects we will discover. Every time I measure more precisely, I'm surprised what I discover. Even the established methods of how to measure the tiny micromotion of these crystals, when we measured it precisely, we discovered that the old model was wrong and we had to refine it. So I don't want to predict the future. What I should say, there's a difference of absolute accuracy and repeatability and precision. This is sometimes confusing because sometimes you might be here limited in absolute accuracy by the unknown of a natural constant, which is constant. And if you measure time, you always get the same reproducible result. And you can use it for quantum sensing, you can use it for a flywheel, for telecommunication, for anything. But you will never know the precise absolute value because you don't know the natural constant. So we have to be careful about what is an absolute claim. The absolute claim will always be higher than the relative measurement. And for many applications, it can go down even to the 10 to minus 21, I would say.
Okay.
Sorry for a long answer.
A quick one, please, over there.
Thank you very much. That's fantastic. There is now the discovery of that transition of a nucleus of about 8 electron volts, so going again to a higher energy scale. And people say because the nucleus is a much less disturbed object than the atomic shell of an atom. What is your take? What is your prediction? How far can, say, this kind of clocks go? It's also an optical clock in some sense. How does it? Can that break the 10 to the minus 18 and 19 barrier and go even deeper? Because you mentioned the stability of fundamental constants. That is also a field of interest. Whether our constants are really constant with time, because it would change our view of the evolution of the universe in some sense.
Yes, I mean, these are many questions in one.
There will be speaker's corner.
Maybe in general, in a snapshot. So thorium is ticking at 148 nanometer. Our clock is ticking at 230 nanometer. So this is not like an order of magnitude. That's a few 10%. So this is not a huge lever, yeah. Where thorium, as you mentioned, is less sensitive to external field because it's a compact nucleus, so the absolute accuracy could go down further. However, there's also a caveat because our clocks at the moment are really limited by a lot of other noise problems, and in particular time dilation. If the particle is moving, yeah, even at microkelvin temperatures, you do get motional time dilation. Yeah? And this is the same for any clock, also for a nuclear clock. So when we're cooling, and if you're cooling a thorium crystal to the millikelvin, you're limited at 10 to minus 18. So there's a very complex question that you raised, and I'm happy to discuss that in a corner. But it's not black and white, so they will have to deal with all the other systematics that we also have.
Okay, thank you. Thank you. Okay, we now move on to the final talk of this session, which will be presented by Richard Norty from Delft University of Technology. His title is Breaking the Wall of Miniaturization in Nanotechnology. Please.
Yep, thanks for this invitation. Today I want to talk about some research we've been doing in our labs. And for decades, usually the question is how small can we make nanotechnology? And one of the questions we've been asking is how big can we make it? And so one way to answer why this is actually an important question, we can look 65 years before when this age of the space exploration. So this shows you more or less all the different space missions we've done over the last 65 years since we started going out into space, a few to Mars, a few to the moon. And if you look out even further, you'll see that there is a handful of human-made objects that have made it out to deeper space, to the outer planets. But if we look on a sort of cosmic kind of scale, we've really haven't gone anywhere. We sent something, Voyager 1 out in 1977, and we just barely left the solar system. And so if you start looking at how long it would take us to get to the nearest star, with any kind of existing propulsion systems, you're talking about 10,000 years to get there, just to the nearest star. And so in 2016, basically thousands of scientists kind of coalesced around a bold idea. And the idea was to use decades of nanotechnology to make, nanotechnology advancements to make microchip satellites. The idea being that we could attach them to large sails, lightweight probe. And the idea being that if we get this small probe with cameras and communication systems and attach it to a large sail that is about 1 gram so about meters in size and nanoscale thickness, that we could, with 10 minutes of laser exposure, accelerate these sails to about 1/5 of the speed of light. And this would essentially reduce our times down from 10,000 years to something about 20 years, about, let's say, a generation. And it's a really, I would say, crazy idea when I first saw this, this proposal, but it definitely got me thinking about what is possible with nanotechnology we have today. But one of the things that people realize is that the light sail is actually one of the hardest components to make. And why is that? Well, if you look at the chip really requires making everything smaller in X, Y, and Z. And that's something we've been doing for nearly half a century. But the sail is a really different component. It's a really different challenge. It's the only nanoscale component that needs to be scaled out to meter scales, right? And that makes it very different from any kind of nanotechnology that we've been doing over the last 50 years. And so right now, our lab is really looking at not just propulsion, but how can we use these things for optical computing, for extreme sensing, where they basically where mirrors are really quite important. Okay, so state of the art, what was actually done when this thing was announced? What was possible? Basically, I would say one of the best materials you can get is thin films of ceramic, which are about 1,000 times thinner than a human hair. And counterintuitively, you would puncture it with holes to make it reflective. So it would basically be reflective at a single wavelength, which is perfect for lasers. It also makes it lightweight if you can remove half the weight with holes. And so basically when it was announced, what we saw is that basically the biggest types of materials, these photonic crystal reflectors, were about fractions of a millimeter size. And so now in our lab, what we've been doing is thinking about so this basically gives you a sense of what those look like. About 300 micron by 300 micron reflectors is what was possible. And now we've been really thinking about the physics of how we manufacture these things. And so here gives you a sense of kind of a comparison. So now we can make these things 60,000 times larger up to the wafer scale. So something that you can really hold in your hand and look at. And this basically essentially gives you some of the thinnest mirrors that you can possibly make. Okay, and so one of the things that now we're looking at in our lab is how to actually show that these things can work. So now what we're doing is we're getting away from this idea of manufacturing something and then taking it into the lab. We're trying to meld these two concepts together. And so now what we're doing is we're actually, for here you can see a wafer. We put it into our machine. We can actually fabricate it, send it into a chamber where we have high-powered lasers. And the idea is to essentially lift these objects stably and lift objects that are about 100,000 times larger than anything that's been levitated with coherent light. So these are really large objects that you can use for sensing, to also kind of look at the dynamics, light-matter interactions. So you can kind of think of it as a rocket that you've chained down, you fired it up, and just to see the dynamics, just to see how this actually works. Okay, but what can we actually do with what we have today? Because we're not making meter-scaled light sails. I think this is actually a really hard challenge. But here, just to show you, these are all the fastest flyby probes to every planet in the solar system so far. The fastest we've ever gotten to Mars is about 4 months. To Saturn, it's about 7 years with Cassini. And Voyager, which has taken about 46 years to get to the edge of the solar system. And so if you take the mirrors we have right now, the reflectors that we have right now, and with about 1,000 times less laser power, we can actually bring these times down quite a bit if you want to take still a 1 gram payload. So the idea being that we can now, for instance, think about sending microchips to Mars in about 32 hours. So about kind of the same way that you send international mail. The other one really nice idea is, for instance, being able to send microchips as you like to Saturn's moons where there's supposedly oceans, about sending one there in less than a month. And the idea of getting to, for instance, to Voyager's position, which has taken us about 50 years, getting there in about 1 year. And that is, I think, incredibly interesting. Yeah, so I think these are big goals. I think you can develop a lot of nanotechnology with these big goals. And it's important to realize that, the first flight was in 1903, just a few feet above the ground there was a plane. And in about 66 years, we were landing on the moon, right? And this is a crazy short time scale. And so I am excited about, essentially this idea of hitting this wall, more or less set by Moore's law, and then what we can really do afterwards when we hit this wall. And I think going upwards is going to give some very interesting results. So thank you.
Thanks, Richard. Are there questions? There's a question.
Thank you. Great talk again. My question is, you probably have to fold the structures you are looking at to transport them to space at some point. Is it something you tried, to have these surfaces and to fold them and maybe...
So actually the idea of this system is more or less, in a way of being able to manufacture things, let's say in low Earth orbit. A lot of these systems actually work in vacuum. They'll have vacuums for free in space, which is great. But this is kind of the idea, is to pre-manufacture these structures in orbit, for instance.
There was a question here.
Yeah, thank you. Great idea. I'm just wondering, assuming that you can send such a chip into space or into the solar system, would it be able to send back any data?
Yeah, this is a really big question, I would say. No, it's a great question, and I would say there's really a whole team of scientists working on this communication system. But that's why, for me personally, I think these shorter missions are really very, very useful, and actually, I would say in some ways one of the more interesting prerequisites, because I think you'll learn a lot from these shorter missions. How do you send back something efficiently? Because Alpha Centauri is really quite a long ways away. Yeah.
Okay. Any? Yeah.
Very short. Just a very short question. What are the estimates of the laser power you would need in order to accelerate these sails?
Yeah. So the idea being on the order of tens of gigawatts of power. Now in the lab, we've actually put about 1/10 of this onto our sails, and we're now figuring out that they actually can survive these laser powers. So one of the big challenges is can you make materials that can survive this and reflect this light, and that's something that we're now answering I think in a good way. But yeah, it's quite a lot of power.
There was a question in the back still.
Yes, thank you for the great talk. So concerning the communication with the system, can you maybe implement not only a sail, but also maybe like a meta surface on the structure? So maybe to have a kind of antenna then for sending signal back?
Yeah, and people have actually proposed this quite a bit, of using the sail itself. And the nice thing about it is that when you have something that's meters by meters, or these large scales, you're talking about trillions and trillions of holes, which means that you can actually functionalize different parts of it because you have so much space to design, which is very different from anything you can do with a nanoscale mirror. That's really something very different. Yeah.
Final one here, please.
Yeah, thank you. My question is, would you also be able to combine the sail with solar cells? Because somehow you need energy.
You could, but they're really different scales. So solar sails are incredibly impressive what they've done these days. So they can make things that are 7 microns thick and meters large. But what we're talking about here, this mass scale is very, very different. We're talking about something that's about order of magnitude smaller than, or 2 orders of magnitude smaller than a solar sail. So it's really the one. I mean, if you think about a euro coin is 7.5 grams. We're talking about something that's 4 by 4 meters that needs to be 1 gram. So this is really a nanoscale object. It's not even a micro scale object, a micro thickness object. So maybe it's possible. Sorry, to get to your question, but maybe it's possible to combine in the future. Yeah, could be, but I think they're very different weight scales.
Okay, then let's thank Richard and the other speakers of the session. There's enough time.